US Physics Olympiad, year 2013, USAPHO, Semifinal exam. This exam consists of 6 problems, 4 problems A in the first day and 2 problems B section in the second day. For each day they were given 60 minutes. Problem A1. The flow of heat through a material can be described via the thermal conductivity K. If the two faces of a slab of material with the thermal conductivity K, area A, and the thickness d are held at a temperature differing by delta T, the thermal power P transferred through the slab is P equal Ka delta T over D. The heat exchanger is a device which transfers heat between a hot fluid and a cold fluid. They are common in industrial applications such as power plants and heating systems. The heat exchanger shown below consists of 2 rectangular tubes of length L, width W, and height H. The tubes are separated by a metal wall of thickness D and thermal conductivity K. Originally, hot fluid flows through the lower tube and speed V from right to left, and originally cold fluid flows through the upper tube in the opposite direction, left to right, at the same speed. The heat capacity per unit volume of both fluids is C. The hot fluid enters the heat exchanger at a higher temperature than the cold fluid. The difference between the temperatures of the entering fluids is delta Ti. When the fluids exit the heat exchanger, the difference has been reduced to delta Tf. It is possible for the exiting originally cold fluid to have a higher temperature than the exiting originally hot fluid, in which case delta Tf less than 0. Assume that the temperature in each pipe depends only on the lengthwise position, and consider transfer of heat only due to conduction to the metal and due to the bulk movement of fluid. Under the assumptions in this problem, while the temperature of each fluid varies along the length of exchanger, the temperature difference across the wall is the same everywhere. You need not prove this. Find delta Tf in terms of the other given parameters. US Physics Olympiad, year 2013, USAPHO, Semifinal exam. Problem A2. A solid round object of radius r can roll down an incline that makes an angle theta with the horizontal. Assume that the rotational inertia about an axis through the center of mass is given by formula I equal beta m r square. The coefficient of kinetic and static friction between the object and the incline is mu. The object moves from rest through a vertical distance h. Question A. If the angle of the incline is sufficiently large, then the object will slip and roll. If the angle of the incline is sufficiently small, then the object will roll without slipping. Determine the angle theta c that separates the two types of motion. Question B. Derive expressions for the linear acceleration of the object down the ramp in the case of I, rolling without slipping, and I2, rolling and slipping. US Physics Olympiad, year 2013, USAPHO. Semifinal exam. Problem A3. A beam of muons is maintained in a circular orbit by a uniform magnetic field. Neglect energy loss due to electromagnetic radiation. The mass of the muon is equal to 1.88 10 power negative 28 kilograms. Its charge is negative 1.602 10 power negative 19 coulomb, and its half-life is 1.523 microseconds. Questions. Question A. The speed of the muons is much less than the speed of light. It is found that half of the muons decay during each full orbit. What is the magnitude of the magnetic field? Question B. The experiment is repeated with the same magnetic field, but the speed of the muons is increased. It is no longer much less than the speed of light. Does the fraction of muons which decay during each full orbit increase, decrease, or stay the same? The following facts about special relativity may be useful. First, the Lorentz factor for a particle moving at a speed v is gamma equal this expression. The Lorentz factor gives the magnitude of time dilation, that is, a clock moving at a speed v in a given reference frame runs slow by a factor gamma in that frame. The momentum of a particle is given by E as a vector equal gamma m v as a vector, where m does not depend on v. The Lorentz force law in the form dp over dt as a vector equal q multiplied by E electric field plus cross product of v and the magnetic field B continues to hold. US Physics Olympiad, year 2013, USAPHO Semifinal exam. Problem A4. A graduated cylinder is partially filled with water. A rubber duck floats at the surface. Oil is poured into the graduated cylinder at a slow, constant rate, and the volume marks corresponding to the surface of the water and the surface of the oil are recorded as a function of time. Water has a density of 1 gram per milliliter. The density of air is neglectable, as are surface effects. Find the density of the oil. US Physics Olympiad, year 2013, USA PHO, Semifinal exam. Problem B1. Shown below is the Blackbird, a vehicle built in 2009. There is no source of stored energy such as a battery or gasoline engine. All of the power used to move the car comes from the wind. The only important mechanism in the car is a gearbox that can transfer power between the wheels and the propeller. The Blackbird was driven both directly downwind and directly upwind, as shown below. In each case, the car remained exactly parallel or anti-parallel to the wind without turning. The tests were conducted on level ground, in steady uniform wind, and continued long enough to reach the steady state. When driving downwind, the builders claimed that they were able to drive faster than the wind, that is, with a speed v greater than speed of wind, so that the car experienced relative headwind while traveling. Commenters on the internet claimed, often angrily, that this was physically impossible and that the Blackbird was a hoax. Some commenters also claimed that the upward case was physically impossible. Question A. Consider first the downwind faster than the wind case. Is the motion actually possible as claimed? If not, offer a brief explanation. If the motion is possible, is power transferred from the propeller to the wheels or vice versa? If the motion is possible, what ground speed is attained? For this question, suppose that when transferring power in either direction between the propeller and the wheels, a fraction alpha of the useful work is lost. Let the wind speed be Vw. Neglect all other losses of energy. Question B. Answer the previous question for the upwind case. US Physics Olympiad, year 2013, USAPHO, semifinal exam. Problem B2. This problem concerns three situations involving the transfer of energy into a region of space by electromagnetic fields. In the first case, that energy is stored in the kinetic energy of the charged object. In the second and the third cases, the energy is stored in the electric or magnetic field. In general, whenever an electric and the magnetic field are at an angle to each other, energy is transferred. For example, this principle is the reason electromagnetic radiation transfers energy. The power transferred per unit area is given by the Poynting vector S equal 1 over mu0 multiplied by a cross product of electric and magnetic fields. In each part of this problem, the last subpart asks you to verify that the rate of energy transfer agrees with the formula for the Poynting vector. Therefore, you should not use the formula for the Poynting vector before the last subpart. Part A. A long insulating cylindrical rod has radius r and carries a uniform volume charge density ρ. A uniform external electric field E exists in the direction of its axis. The rod moves in the direction of this axis at a speed v. Question I. What is the power per unit length P delivered to the rod? Question 2. What is the magnetic field B at the surface of the rod? Draw the direction on a diagram. Question 3. Compute the Poynting vector, draw its direction on a diagram and verify that it agrees with the rate of energy transfer. Part B. A parallel plate capacitor consists of two discs of radius r separated by a distance d much less than r. The capacitor carries a charge q and is being charged by a small constant current I. First question. What is the power P delivered to the capacitor? Question 2. What is the magnetic field B just inside the edge of the capacitor? Draw the direction on a diagram. Ignore fringing effects in the electric field for this calculation. Question 3. Compute the Poynting vector, draw its direction on the diagram, and verify that it agrees with the rate of energy transfer. Part C. A long solenoid of radius r has n turns of wire per unit length. The solenoid carries a current I, and this current is increased at a small constant rate dr over dt. First question. What is the power per unit length P delivered to the solenoid? Question 2. What is the electric field E just inside the surface of the solenoid? Draw its direction on a diagram. Question 3. Compute the Poynting vector, draw its direction on a diagram, and verify that it agrees with the rate of energy transfer.